From space, the tropical ocean almost peaceful, a blue surface hiding the first clues of a storm. At water level, the calm feels misleading because the heat beneath, it is already waiting to rise. Sunlight warms the sea surface, and invisible vapor begins lifting ocean energy into the humid air above. A shallow layer of warm water can influence clouds across distances larger than many American cities. Small thunderstorm towers appear over open water, looking isolated, before the atmosphere starts connecting them together. The wind may seem like the beginning, but the storm's first fuel is drawn from below the surface. As moist air rises, scattered clouds grow taller, turning warm vapor into the first organized storm cells. Satellite loops and radar screens reveal patterns long before anyone onshore can feel the coming wind outside. On the coast, ordinary streets wait under bright skies for changes that began far offshore hours earlier. The quiet question is simple. Why does warm water matter enough to build something this powerful overhead? A distant patch of ocean becomes personal when its heat starts moving toward homes, roads, and families. Outer rain bands can reach land early, warning that the storm's center is not the only threat. Warm water helps, but hurricanes also need moisture, unstable air, rotation, and weak disruptive winds above. The disaster people remember begins as invisible energy, long before broken trees or flooded streets appear later. To understand the monster, we first have to follow heat as it turns into organized motion. Chapter 1 begins at the surface, where warm ocean water becomes the storm's main fuel supply. Each ripple releases moisture into the air, slowly loading the lower atmosphere with invisible water vapor. Think of the warm ocean like a fuel tank, except the fuel rises as humid air. Evaporation moves heat from sea to sky, giving the developing storm something it can keep using. Buoys, satellites, and aircraft measure ocean heat because forecasters need to know what fuel is available. Across warm tropical waters, the atmosphere finds broad zones where storms can form and survive longer. From a beach or fishing boat, this fuel source may look like nothing more than calm water. Wind lifts spray from the surface, adding more moisture to air already thick with tropical humidity. Warm, moist air rises because it is lighter than the cooler air pressing around it from all sides. As the air climbs, cloud towers grow upward, carrying ocean heat into the lower sky above. Rain does not simply end. The process condensation releases hidden heat back into the growing storm. That released heat helps more air rise, pulling additional moisture from the warm ocean. Below it, scientists watch from satellites and aircraft searching for structure inside what first looks chaotic and scattered. One rising column is small, but many can begin shaping a weather system hundreds of miles wide. Once enough air rises, the next mystery is what happens to pressure near the warm surface. As air lifts away from the ocean, pressure near the surface begins to fall slightly below normal. Nearby air responds by moving inward, trying to fill the space where pressure is lower there. The rougher water becomes, the more contact grows between the sea surface and the moving air. Tiny exchanges at the surface can connect directly to towering clouds far above the darkening ocean. Separate storm cells may begin feeding one another, sharing moisture, heat, and inward moving air over water. A hurricane is not one cloud, but a feedback system repeating the same process faster and wider. Floating buoys and research aircraft sample wind, pressure, and water conditions while the system grows offshore. Forecasters asked whether scatter storms are staying separate or beginning to organize around a common center. When organization improves, the risk increases for stronger winds, heavier rain, and expanding ocean surge later. But inward, moving air is only part of the story. The storm still needs rotation to strengthen. Warm water creates a wide feeding zone, letting storm clouds keep drawing energy from below continuously. Moisture transfer is not a single explosion, but a steady exchange between ocean and atmosphere overhead. For development to continue, heat and moisture must persist long enough for rising air to rebuild. Tall cloud tops show energy moving upward from warm water into the highest storm layers above. Scientists look for curved bands, cooling cloud tops, and pressure changes that signal real organization beginning. A tropical system can become dangerous before it looks like the perfect spiral on television forecasts. Repeated storms over warm water can load the atmosphere with rain before landfall ever begins nearby. What starts as scattered thunderstorms can eventually cover a region as large as an American state. Heat, moisture, pressure, and wind must reinforce one another, or the young storm quickly falls apart. Next, those thunderstorm towers become the engines that decide whether a disturbance can truly intensify further. Why do scattered tropical storms sometimes become the first pieces of something far larger, over warm water below? The open sea keeps breathing moisture upward, feeding young cloud towers before any clear spiral appears above the horizon. Warm surface air rises first, pulling vapor into updrafts that begin the storm's vertical engine above the sea. As vapor climbs higher, it cools into droplets, turning invisible humidity into towering white cloud material above the ocean. Condensation does not just make clouds. It releases hidden heat back into the growing storm engine above the ocean. One tiny phase change seems harmless, but repeated billions of times, it can build skyscrapers of cloud overhead. A new thunderstorm tower throws its shadow across water, still feeding it from the warm surface beneath the clouds. Before satellites see organization, instruments already measure heat, humidity, and pressure changing over the open ocean before dawn. Rain can look like release, yet inside the cloud, it may signal heat being added again inside today. The mystery is whether these separate towers fade apart or begin acting like one larger system over water. Several storms can rise together, but only a few clusters survive long enough to organize further over water. Clouds pulse over the warm ocean as old storm outflows collide and trigger new vertical growth around it. Cool air spilling from one storm can lift nearby humidity, sparking another tower beside it again overhead nearby. When pressure dips near the surface, surrounding air has more reason to gather and rise upward nearby again. As that pressure falls slightly low, level winds begin sliding inward across the warm ocean skin toward the clouds above. A storm cluster can spread beyond a city, yet still depend on invisible vapor rising below every minute. On radar, the first clue may be repeated storm bursts, not a clean hurricane spiral yet on screen. A tropical disturbance is not one storm, but a crowded neighborhood of storms trying to organize together overhead. Anvil clouds spread high overhead, while the lower storm keeps drawing warm moisture from the sea below again. If exhaust escapes above the cloud tops, the whole system can keep breathing and growing upward for hours. Why do some tropical clusters collapse quickly, while others survive the night over open? Water longer offshore again. A developing storm needs rising air below and enough upper outflow to vent heat away efficiently above it. The strongest updrafts punch cloud tops upward, marking where warm air is climbing fastest today, above water clearly. High inside the cloud, droplets freeze into ice, releasing more heat through another hidden atmospheric step aloft again. That released heat can lower nearby pressure, encouraging more surface air to flow inward again toward clouds nearby. Small storms begin linking into curved bands, suggesting the weather is becoming more than scattered cells overhead now. Forecasters watch for pressure drops, wind shifts and structure, before naming a stronger tropical system officially at sea. The storm's power is not only overhead. Surface winds help gather more fuel from below, over water. Below the waves, mixing decides whether the storm keeps warm fuel or stirs up cooler water below it. If cooler water reaches the surface too soon, the young storm can lose strength before organizing at sea. When does a storm cluster become a system with a center forecasters can actually track clearly from space? The cloud field begins leaning toward one shared region where pressure is quietly falling below it slowly. Now, a falling pressure reading may be small, but it shows the atmosphere beginning to reorganize itself from within. Lower pressure does not suck air like a vacuum. Air simply moves toward that lower zone across water. As more air converges, more moisture rises, reinforcing the loop above warm ocean water below. And again there, a research vessel looks tiny beneath a cloud wall tall enough to dwarf downtown buildings inland by comparison. Forecasters look for closed circulation, not just bright cloud tops, before a storm earns its name at last. The tallest tower can be impressive, but organization matters more than one explosive burst of cloud by itself. Curved rain bands begin, moving heat inward, while spreading the storm's reach across the sea around it. It is not a hurricane yet, but the first rough blueprint is becoming visible overhead for forecasters now. What separates weak tropical weather from the beginning of a storm people must track seriously from home now. The ocean keeps feeding moisture upward as rain bands stack repeatedly over the same broad region below it. Every raindrop returns water downward, while vapor above rises again to feed the cloud cycle above the sea. Evaporation, condensation, and rainfall form a loop, but warm water keeps pushing energy upward constantly from below again. And buoys and satellites reveal whether the ocean still holds enough heat to support further growth at sea today. One weakening tower does not always mean failure. Another cell may be taking over nearby instead very soon. The system begins when individual towers reinforce the larger circulation, forming slowly around them together at last now. For coastal families, this distant organization is when an ocean disturbance starts feeling personal again at home. Now, the next step is not simply more cloud, but a shape beginning to rotate slowly around a center. Once the clouds wrap inward, the hurricane story enters its next and stranger phase. Spin begins at last. Inside each tower, vapor turns back into rain, releasing heat that keeps the storm cluster breathing upward again. One thunderstorm is weather, but dozens working together can become something far larger over the open ocean below. As warm air rises, pressure near the surface falls, inviting more air to rush inward beneath growing clouds. The real threat is not a single dark cloud, but many storms beginning to cooperate overhead across the warm sea. Now the mystery changes. Why does this growing tower field start turning instead of spreading apart over the sea? If air is mostly rising upward, why does the whole storm begin organizing into a rotating shape above water? Air near the ocean surface moves toward lower pressure, feeding the developing center from every side around it. It's just above the waves. Winds begin leaning inward, dragging spray toward the storm's hidden low beneath thickening clouds. On a pressure map, the air no longer spreads evenly. It gathers around one troubled area over the sea. But inward motion alone cannot the hurricane. The moving air also needs to curve around the center. This storm is not forming on a flat table, but on a spinning planet beneath it, slowly turning. As Earth rotates, moving air appears to bend, shaping the storm without pushing it directly across the ocean. Forecasters watch that bend in satellite loops, where cloud bands begin tracing a loose spiral over open water. The first curved bands are clues. Separate storms are starting to share one center over open water. Coriolis does not create the hurricane, but it helps organize motion already moving inward toward the center below. As air keeps converging, its path wraps around the low instead of entering straight through the center. Below, the ocean surface shows the change first, with streaks of foam pointing in different directions beneath clouds above. Clouds above and waves below begin responding together, as if the whole system found rhythm over warm water. One rain band can stretch beyond a city skyline, then reach across open water for miles without warning. But can these curved bands close around a center, or will the system tear apart over open water? From above, the cloud shield still looks uneven, yet the bands are no longer random across the tropics. The rain bands become feeding arms, pulling warm moisture inward from the surrounding sea toward the center below. When surface winds keep converging, the storm receives a steady supply of warm, humid air from the sea. At human scale, this organization arrives as sudden gusts, hard rain, and fast, changing skies over ordinary streets nearby. The storm must organize inside a larger atmosphere, where dry air or shear can disrupt it overhead quickly. Ocean buoys feel the change directly, recording falling pressure and winds that keep shifting direction beneath the storm. Before a storm looks circular, its true center may remain broad, messy, and hard to locate for forecasters. When inflow persists, the broad low can tighten into a more coherent, rotating circulation around the center below. The system is close to becoming one machine, with many moving parts feeding the same center over water. The next question is simple and dangerous. What happens when pressure falls even farther within the center area? Lower pressure near the center encourages surrounding air to move inward faster and more continuously from every side. Near the surface, that inward pull roughens the sea, calming waves beneath the cloud shield under the storm. Drawn inward, air rises, cools, condenses, and builds new towers that release more heat inside the storm again. Aircraft instruments can fly through the developing storm, measuring pressure changes hidden inside clouds above the ocean's surface. Inside the storm, organization feels chaotic turbulence, gray walls, sudden drops, and almost no horizon outside the windows. A lower pressure number can signal that the storm is becoming stronger, tighter, and better organized over open water. Cloud bands now follow curved paths, bending toward a core that is still forming within the storm's circulation. Inside the thick cloud shield, visibility can shrink to less than a single neighborhood block during the flight. Near the surface, air flows inward, high above. Outflow helps the storm breathe outward around the system below. The storm is nearing a structure that can support stronger winds around its developing core over warm water. Radar can reveal bands wrapping around a broad center, even when satellites show only cloud within the storm. The outer bands already carry heavy rain and gusts far from the future center. Over coastal waters nearby, spiral bands work like feeding corridors, guiding warm, moist air toward the storm's interior again and again. That feeding structure can span distances larger than many states, even before landfall is certain across the basin. For people watching forecasts, those outer bands are often the first warning of trouble along the coast nearby. A dangerous storm does not need perfect symmetry. Rough organization can still hide serious growth inside the clouds. As inflow bands feed the core, moisture and heat keep arriving from the warm sea again from below. Inside the core region, movement becomes dense and layered, with clouds racing past each other through thick gray layers. The storm now links surface inflow, rising towers, and high outflow into one connected engine over the ocean. Next, that engine begins tightening toward the violent structure that may become an eyewall in the next chapter. The spiral is not decoration. It is the storm arranging heat, pressure, and inflow into one moving system. On radar, separate rain bands begin wrapping around a center, showing the storm is no longer scattered. From above, the circulation stretches across hundreds of miles, larger than many states people recognize on maps. Long before landfall, outers are already feeding warm moisture inward from the ocean's restless surface. As pressure falls near the center, surface winds pull more humid air into the growing spiral. Near the ocean, air flows inward, high above, outflow spreads, letting the storm breathe vertically through layers. A center is taking shape, but the most violent ring of the hurricane has not formed yet. Forecast attention changes when scattered storms become one organized tropical cyclone, moving across warm water together. To understand the danger, we now move from the spiral shape into its inner core. Why would falling pressure create a quiet center surrounded by the storm's most violent winds? The Eyewall rises around the center like a circular mountain range made of rain and cloud. Hurricane hunter aircraft fly into places too dangerous to understand from radar images alone, measuring the core directly. Inside the Eyewall, winds accelerate, rain thickens, and rising air becomes brutally concentrated around the center. The center can turn strangely calm because air sinks inside the eye and clouds thin away. That calm is temporary around the rim. The strongest winds wait like a moving wall nearby. Air rises around the Eyewall. While sinking air clears the center and opens the eye below. A drop zone falls through the storm, measuring pressure, humidity, temperature, and wind as it descends toward water. An eye can span a city, yet shift quickly enough to change danger block by block. How can the quietest space in the hurricane sit directly beside its most violent wall of wind? The eye is only one chamber inside a much larger machine, moving heat and water outward. From space, the hurricane looks orderly, but each ring performs a different job. Inside the circulation, spiral bands carry heat, moisture, and momentum inward, feeding the engine around the eye continuously below. Near the ocean surface, friction bends the wind and helps shape the storm's inflow path. Air spirals inward low, rises through thunderstorm towers, then exits outward high above the storm system. The center track is useful, but it never shows the full reach of damaging winds outward. Impacts spread across wide zones, sometimes far from the thin line people watch on forecasts at home. Outer bands can reach the coast hours before the eye, bring squalls, flooding, and sudden gusts. A single neighborhood may sit beneath only one edge of the storm's enormous circulation field. When a hurricane becomes lopsided, danger can shift away from where people expect it most clearly. The storm's shape depends on the surrounding atmosphere, not only the ocean beneath it directly. What happens when fast winds high above, pushing against the storm's vertical tower from above? Strong wind shear can tilt the cyclone, disrupting the organized heat engine inside it very quickly. When thunderstorms drift away from the center, the storm may struggle to strengthen further over water. But a ragged storm can reorganize if ocean heat and upper winds align again later tonight. Birds, insects, and coastal animals may react to pressure and wind changes before landfall ever arrives. The coastline starts changing early as surf rises and water moves against beaches and inlets steadily. Eyewall clouds can tower far above ordinary storms. People watch from backyards and highways below them. After the eye passes, winds can return violently from the opposite direction without warning at all. That dangerous pause can fool people into stepping outside before the hurricane is truly finished moving through. The eye teaches the hurricane's central lesson. Structure controls where danger appears first on land. Falling pressure is one important sign. The inner core may be tightening and strengthening very quickly. A steeper pressure gradient helps accelerate winds around the eye, turning pressure directly into violent motion. The eyewall concentrates rising air, heavy rain, and violent wind inside one rotating ring of clouds. At human scale, the storm becomes pressure, water, debris, and droplets striking like gravel outside homes. The eye looks peaceful because the most violent motion has shifted around its rim instead completely. If the inner core stays organized, the next threat is rapid strengthening over warm water ahead. The heat below the surface can decide whether churned water cools the storm or feeds it. Now the story moves from storm structure to the deeper fuel waiting under the waves below. What happens when a well-built hurricane crosses water warm enough to keep feeding it further? The next chapter follows the moment. Forecasts can change faster than coastal communities expect overnight together. The forecast room shifts from the storm's outer spiral to the tighter signals forming near its hidden core. On radar, pressure contours crowd together, warning that the eyewall winds may be tightening with the center. Inside the storm, hurricane hunters feel the evidence that satellites can only measure from far above. The eyewall rises like a moving stadium of rain, where air climbs fast and winds accelerate. The eye may appear strangely peaceful, but the storm's strongest violence is circling just outside it. As a drop sonde falls, it records pressure, wind, humidity and temperature through the storm's vertical maze. Around the eye, rising air feeds the wall, while sinking air helps clear the center from within. Compared with the whole storm, the inner core is small, yet it can decide the worst damage. So why can a smaller, tighter hurricane core sometimes signal a greater threat to the coast? The storm now looks organized enough that its next major change may arrive faster than expected. Satellite bands wrap inward, showing separate cloud towers can begin acting like one connected machine. Each curved band carries heat, moisture and wind toward a center that keeps tightening over water. A hurricane structure matters because the same category can hide very different inner core behavior and risk. When the eyewall leans, breaks, or rebuilds, the storm's strength can shift in complicated ways. Some powerful hurricanes replace their eyewalls, briefly weakening before a wider wind field spreads outward again. This process does not happen in every storm, but when it does, forecasts become more difficult. The eye's size can change, and with it, the location of the most destructive winds. A wider eye may look less intense, yet dangerous winds can cover a much larger area. The camera pulls back from rain bands reaching far across the open ocean. Those bands are not decoration. They move heat, momentum, and rainfall around the hurricane's engine. Near the ocean's surface, inflow winds keep dragging warm, humid air into the storm's circulation. High above, outflow spreads like an exhaust system, helping the hurricane breathe upward and outward efficiently. If that exhaust is blocked by wind shear, the storm can struggle to stay organized vertically. But under low shear, the vertical tower can remain stacked, letting the engine run more efficiently. This is why two storms over warm water can behave very differently in the same basin. One storm may collapse under hostile winds, while another finds the atmosphere arranged almost perfectly overhead. In that rare alignment, the hurricane's core can tighten, while pressure begins dropping more quickly. The warning signs are subtle at first, appearing as cleaner symmetry and colder cloud tops above. Forecasters watch these changes carefully because small inner core improvements can become major intensity shifts overnight near land. The eye and Eyewall have revealed the machine. Now, the question becomes how fast it can deepen. Rapid intensification begins when the storm finds fuel, structure, and atmosphere working together at once over water. Warm surface water matters, but deeper ocean heat can keep feeding the storm after waves mix the sea. As the hurricane churns the surface, cooler water can rise and weaken the heat supply below. If deep warm water remains underneath, that cooling effect may not slow the storm enough at all. Across the Gulf, warm layers can extend downward, creating a thicker reservoir of potential storm energy. The storm does not know the map, but its winds respond to the heat beneath it. When pressure falls quickly, aircraft instruments can show the storm strengthening before land radar sees everything. Satellite loops may reveal a colder, taller cloud ring wrapping tighter around the emerging eye above water. That ring suggests stronger updrafts, but it still needs real measurements to confirm intensity changes inside. The forecast challenges timing because a storm can change faster than evacuation. Plans can adapt. Low wind shear lets the hurricane's heat engine stay upright instead of being torn apart. Moist surrounding air also matters because dry air can erode thunderstorms inside the hurricane core quickly, even with warm water. A disorganized core may fail to intensify as models first suggest at first. But once the core becomes aligned, each burst of convection can reinforce the next one upward. The storm's pressure drops, winds rise, and the forecast discussion becomes more urgent for everyone watching. Rapid strengthening can turn a distant concern into a serious decision made overnight. A small change near the eye can alter risk for millions along a forecast coastline. Quickly, can the hurricane keep strengthening before land finally cuts off the ocean heat feeding it below? Aircraft data now tests whether the satellite's alarming shape matches the storm's real strength. The next question is not only how strong it becomes, but what that strength means at landfall. Deep, warm water can keep feeding a hurricane, even after its own winds churn the surface colder. Below the waves, a deeper reservoir of heat may still wait beneath the storm's spinning engine. When that heat reaches rising air, the pressure can drop faster than coastal forecasts expected overnight. The storm does not simply grow wider, its strongest core can tighten like a turning gear. Hurricane hunters fly toward that core because their instruments can reveal changes satellites cannot fully measure from orbit. Each pressure reading becomes a clue, showing whether the atmosphere is organizing or beginning to break apart. A falling central pressure often means the storm is drawing more air inward with increasing force. But rapid intensification needs more than warm water that the upper winds must avoid tearing the tower apart. When wind shear stays low, thunderstorm towers can wrap closer around the center instead of scattering downwind. In that narrow window, the ocean and atmosphere begin cooperating with a sudden and dangerous efficiency. The eyewall can contract inward, concentrating violent winds around a smaller ring of towering, rising clouds. That smaller ring may spin faster, like a skater pulling both arms closer to the body. From space, the storm's eye can sharpen while colder cloud tops bloom brighter around it. To people on the coast, that satellite change may mean evacuation time is quickly shrinking now. Rapid strengthening is most dangerous when it happens near land with little room left for adjustment. Forecast models may agree on the track, while still struggling with how strong the storm becomes. A few miles of track matter, but a few hours of strengthening can change almost everything. Emergency managers watch pressure, wind speed, surge forecasts, and timing, all moving together under serious uncertainty. The cone shows where the center may go, not where every dangerous impact will happen around it. Outside that line, rain bands and surge can still reach neighborhoods that felt safely removed earlier. As the storm approaches shallow coastal water, its winds begin piling the ocean toward nearby land. This is storm surge, not a tsunami, and it can arrive as a rising wall of water. Low pressure helps lift the sea slightly, but wind pushing water is the far larger danger. A coastline shaped by bays and inlets can funnel surge into neighborhoods like water into a narrowing hallway. On a flat barrier island, a few extra feet can cross roads, yards and first floors. Waves ride on top of the surge, adding pounding force to water already moving inland quickly. For many coastal homes, the first disaster is not wind, but saltwater entering from below tonight. Road signs, docks, and parked cars become scale markers as water turns familiar streets into channels. The same ocean that fed the storm now follows it inland, pushed by sustained wind today. Even before the eye arrives, outer bands can flood streets and weaken major escape routes inland. Rain can fall in bursts, pause briefly, then return harder as another band rotates through again. When drainage systems fill, ordinary intersections can become dangerous pools within only a few minutes outside. Inland, the storm loses ocean fuel, but it may still carry enormous moisture overhead above cities. That moisture can fall over hills and neighborhoods far from the coastline people watched earlier. A weakening hurricane can still create a freshwater flood disaster long after landfall headlines begin fading. At landfall, the storm begins losing its fuel, yet its stored momentum still reaches the shore. Palm trees bend first, but the real story may be water rising silently behind them now. The coastline becomes a collision zone, where ocean energy meets roads, homes, dunes and seawalls directly. In the Eyewall, rain moves sideways and visibility can vanish within a single city block quickly. Then the eye may pass overhead, bringing an eerie pause that is not the storm's end. People who step outside too early may meet the opposite eyewall arriving from another direction soon. Behind the calm, the second half of the storm can strike damaged buildings even harder afterward. As the center moves inland, trees, power lines, and saturated soil become part of the hazard. Wind opens the first wounds, but rain and flooding can decide how long recovery lasts afterward. Rivers may keep rising after the sky begins clearing, because upstream rainfall is still draining downward. A hurricane's danger spreads through connected systems coast, roads, power, rivers and neighborhoods inland together. That is why landfall is not a finish line. It is a change in the disaster's shape. The storm weakens without warm water, but its water can keep moving through the landscape afterward. By the next morning, satellite images may show a broken storm over flooded towns below inland. What began as ocean heat now remains as inland water, damaged streets and questions still unfolding. The shoreline appears first as a thin grey line, but the hurricane has already pushed the ocean toward it. Storm surge is not a wave arriving once, but a rising wall of water driven inland by wind. Along the barrier island, dunes that look permanent begin breaking under hours of water and pressure. A few feet of surge can turn familiar streets into canals, hiding curbs, drains and dangerous debris. The wind gets attention on camera, but water often decides which neighborhoods become impossible to reach. As the eye nears land, air rushes at the coast with the force of moving machinery. Roofs, signs and trees fail unevenly because wind damage depends on direction, exposure and small weaknesses. Inside the Eyewall, rain does not simply fall. It moves sideways through streets like shattered glass. A house may survive the first gusts, then face water pushing silently through doors and vents. For coastal families, the storm becomes real when the forecast map turns into water at the curb. Farther, rivers wait for a different disaster, one measured in inches of rain, not wind. When rain bands stall over hills and suburbs, flooding can grow long after landfall leaves the news. A weakening hurricane can still carry tropical moisture hundreds of miles from the coastline, soaking places far inland. Inland towns sometimes prepare for wind, then discover that water moving downhill is harder to escape. The storm's shape begins changing over land, but its remaining moisture keeps finding new places to fall. Highways become fragile lifelines when flooded underpasses. Fallen trees and power outages begin cutting communities apart. Emergency crews study the same roads from above, searching for gaps where water has not crossed. A neighborhood may look intact from the air until brown water reveals how much access is gone. The danger moves through systems, from power lines and cell towers to hospitals, pumps and bridges. One failed pump or blocked drainage channel can change the outcome for an entire city block. Storm surge, rainfall, and wind often overlap, making the disaster harder to separate into simple categories. The hurricane's categories measure wind speed, but they do not fully describe flooding risk for every community. That difference matters because a lower category storm can still bring life, threatening water into homes and streets. In flat coastal regions, elevation may change so little that water travels farther than many residents expect. Wetlands and marshes can slow surge, but development often removes parts of that natural coastal defense. Barrier islands take the first strike, absorbing energy while also exposing homes, roads, and evacuation routes. Every evacuation decision is a race between forecast uncertainty and the time required to move people safely. By the time water reaches a driveway, many of the safest choices may already be gone. The storm keeps revealing an uncomfortable true disaster. Is physics meeting where humans choose to build? The coastline is not just a place on a map, it is a system of fragile connections. As the clouds continue inland, meteorologists track the storm's changing center with radar and aircraft data. The forecast battle begins before landfall, while the hurricane is still reorganizing itself over open water. Satellites watch the cloud tops from orbit, but they cannot directly feel the pressure falling inside. That is why hurricane aircraft fly into violent storm places most pilots would avoid entirely. Their instruments measure wind, pressure, temperature, moisture and altitude, turning invisible violence into useful data points. Each pass through the storm adds a clue, but no single measurement explains the whole hurricane. Buoys and ocean sensors reveal whether water below still holds enough heat to feed intensification. Radar near land shows the rain bands tightening, bending, and sometimes training over the same towns repeatedly. Computer models turn these observations into possible futures, each one shaped by different assumptions and uncertainties. The forecast con is a tool for uncertainty, not a picture of the storm's full danger. People often watch the center line, but dangerous impacts can reach far outside that narrow path. A small shift offshore can change who gets surge, while inland rainfall may follow another pattern. Forecasts improve as data improves, yet the atmosphere still changes faster than any map can promise. This is why warnings sound cautious. They must protect people before every important detail is certain. Behind every forecast update is a question with real consequences. Who needs to leave, and when? The storm is no longer only a natural machine. It has become a human decision-making test. On television screens, colored bands look clean, but outside they arrive as noise, darkness, and water. The next chapter follows the people and instruments trying to read that moving chaos in real time. To understand a hurricane forecast, we must see how scientists measure what the ocean keeps changing. The camera pulls from flooded streets back to orbit, where the spiral still hides unanswered motion. Even after the wind fades, floodwater still carries the storm's energy through streets that look strangely quiet. Warnings continue after landfall because rivers, roads, and power lines can remain dangerous long after the center passes. Field instruments keep recording pressure, rainfall, and wind, turning the aftermath into evidence forecasters can still use. A hurricane's reach is not measured only at the beach, but across counties connected by water. So the next question becomes harder. How did scientists see this danger forming before landfall ever happened? From orbit, satellites give the first wide view of clouds gathering over miles of warm ocean. Cold cloud tops reveal towering storms, showing where rising air is punching high into the atmosphere. Far below, ocean buoys feel the storm directly, measuring pressure, wind and waves in real time. Every model begins with a snapshot of the atmosphere, but that snapshot is never perfectly complete. The forecast cone is not a promise of safety outside the line, it is a map of uncertainty. Reconnaissance aircraft enter the storm because some questions cannot be answered from space alone with enough precision. Each instrument drop falls through millimeters of wind, humidity, temperature, and pressure, building a vertical storm profile. Near the core, falling pressure can reveal strengthening before the worst winds reach the waiting coastline. Wind estimates come from satellites, aircraft, buoys, and radar, not from one dramatic image alone today. As the storm nears land, radar begins showing the hidden structure inside the dangerous rain bands. A small shift in steering, winds can move the worst impacts from one town to another. Forecasters compare many models because one confident-looking line can hide a much wider range of outcomes. Evacuation decisions must happen before exact landfall is known, when uncertainty still feels uncomfortably large to everyone. National forecasts become local choices. Through county maps, emergency alerts, and voices people already trust most. For families watching at home, the cone can hide hazards, spreading far beyond the center track. Storm surge needs its own forecast, because coastline shape can decide where water piles highest inland. A shallow continental shelf can let wind-driven water rise higher before it reaches the vulnerable shore. Barrier islands and bays can redirect surge, pushing ocean water into places that once seemed protected. Rainfall forecasts follow the bands, not just the eye, because flooding often travels far inland afterward. Freshwater flooding can peak after the strongest winds fade, when rivers keep collecting the storm's rain. A single warning message must combine wind, surge, rainfall and timing without making the danger confusing. Behind each evacuation order, officials weigh roads, shelters, hospitals, and the hours people need to move. When the track shifts, one town may breathe easier, while another suddenly enters the danger zone. A correct forecast can still fail people if the warning is misunderstood, delayed, or ignored locally. Forecasting is not only a scientific system, it is a human network stretched across the storm. Some hurricanes change faster than expected, forcing urgent updates, while communities are already making difficult decisions. Aircraft data can sharpen forecasts over open water, where surface observations are dangerously sparse and limited. Data assimilation means the mocked it with fresh observations before it predicts the next hours. Ensemble forecasts do not choose one future. They show a family of possible storm paths ahead. Raw model lines can look precise online, even when the real message is probability and uncertainty. Modern warnings focus on impacts because the center track alone does not describe what people face. Sudden strengthening can compress the warning timeline, leaving less time for trust to become action fast. More observations improve the picture, but they cannot remove uncertainty from a chaotic atmosphere completely yet. Even with satellites and supercomputers, the atmosphere keeps small details that can grow into major changes. The forecast battle is partly against the storm and partly against the clock before landfall begins. Inside the forecast room, ocean physics becomes guidance that families, mayors and emergency crews must use. Early warnings can feel excessive under calm skies, but waiting for proof can make action impossible. Trust is built when uncertainty is explained before the storm, not after the forecast changes suddenly. Even the best forecast still depends. People leaving early, preparing supplies and listening carefully afterward. Forecasting continues after landfall because rain bands, rivers and weakened structures can still create emergencies inland. Far inland, the storm's rain can turn creeks and roads into hazards miles from the coast. When men the Aiken, the visible monster shrinks, but its water can keep moving through the landscape. That is why the next question reaches beyond one storm toward the heat stored in the ocean. Short-term forecasts track one hurricane, while long-term ocean patterns ask how future risks may change next. In one raindrop on glass, the storm's forecast points back to the ocean that fueled it. The cone shows where the center may travel, but the storm's danger often spreads much wider. Many people watch the center line, while flooding, wind, and tornadoes can unfold far outside it. At home, families read changing alert phones and televisions, trying to understand uncertain timing before nightfall. With every new observation, the forecast sharpens, but the atmosphere never becomes perfectly still or simple. Pressure, wind, humidity readings give forecasters a clearer picture of the storm's inner machinery over water. From space, the cloud shield can stretch wider than several states, hiding hazards far from landfall. Warnings matter early because dangerous water and wind can arrive before the eye reaches shore itself. A forecast becomes real on evacuation highways, closed bridges and low roads already taking rising water. The question is no longer only where the storm goes, but how much energy it carries. Outer rain bands sweep inland, while computers, aircraft and satellites keep fighting to define the storm. Officials must act before certainty arrives, because moving thousands of people takes more time than forecasts allow. On the ground, one forecast line becomes miles of headlights moving away from vulnerable coastal water. Surge warnings translate wind, pressure and coastline shape into water heights people can actually understand before landfall. Buoys feel the ocean directly, while satellites watch the storm's enormous structure from far above Earth. No single instrument sees. Everything but thousands of small measurements can build one larger storm picture. The clearest warning is not always dramatic. Sometimes it is a plain map with honest uncertainty. When a storm changes quickly, late warnings can turn ordinary choices into urgent, narrowing paths ahead. A falling sensor briefly enters the storm's hidden layers, measuring pressure, wind and moisture in darkness. Those measurements point back to warm ocean water, the fuel beneath the entire rotating system below. If that fuel tank changes, the challenge of warning coastal communities changes with it too tomorrow. After landfall, the ocean can look peaceful again, even while heat remains below the surface unseen. Surface warmth matters, but deeper stored heat can keep feeding storms when waves churn the sea. Across the Gulf, a small temperature difference can cover water larger than many American states combined. Scientists track ocean heat because hurricanes do not respond only to the skin of the sea. Sometimes a storm weakens itself by stirring colder water upward and cutting off its ocean fuel. But when warmth reaches deeper, the churning may not cool the storm's engine fast enough anymore. For coastal resid heat is not abstract data, it becomes preparation, insurance and evacuation timing. Wetlands and barrier islands can absorb energy, but they are fragile defenses under repeated, powerful storms. When more buildings rise near low water, the same hurricane can create far greater losses later. Risk is not made by weather alone. It forms where water, land, and human choices meet. A warmer atmosphere can hold more moisture, giving storms more rain to release over land below. As moist air rises and cools, stored vapor condenses into the heavy rainfall people remember afterward. Some hurricane disasters unfold inland after the cameras leave the beach, and rivers keep rising relentlessly. A hurricane does not need a coastline nearby to flood towns, roads and mountain valleys inland. Healthy wetlands can slow water and store it, making ecosystems part of the safety system too. Risk maps connect storm science with homes, roads, drainage systems, and the choices made after rebuilding. Preparation is not only leaving early, it is rebuilding wisely before the next warning appears again. Just a few feet of water can change the future of an entire city block forever. Disaster grows when natural hazards meet vulnerable places, not from physics alone or chance alone either. The hard question is not whether hurricanes happen, but how communities choose to live with them. When the water pulls back, the storm leaves damage, measurements and memory for the next forecast. High watermarks turn perseverance into useful data, guiding future maps, warnings, and rebuilding choices ahead. From orbit, a weakening hurricane still carries huge moisture fields across states far from the coast. The calm surface after one storm can still help set conditions for another one later on. The machine runs when heat vapor, pressure and rotation align over warm ocean water together naturally. For coastal families, hurricane science becomes personal after the forecast cone disappears from the screen again. Dunes, wetlands and reefs are not scenery. They are living pieces of coastal defense for communities. Changing risk asks planners to look beyond the last storm and imagine the next shoreline ahead. To answer the hurricane question, we return to the warm ocean that started everything below us. if the ocean is the fuel tank, tomorrow's storm may begin before any clouds appear overhead. The same hurricane can cause different disasters depending on what people have built beside the water. From street level, the coast looks flat and familiar. From above, its hidden elevation risk appears. For families near the Gulf, hurricane science becomes windows boarded, routes checked, and choices made early. Marshes, dunes, and wetlands cannot stop every surge, but they can slow water and absorb force. The beaches people love can also become the places where surge, erosion, and overwash arrive first. Risk is not just the storm itself. It is the storm meeting everything in its path. On older coastal streets, high watermarks and repaired roofs show how past storms quietly remain visible. A forecast only becomes real protection when communities have time, trust, roads, and resources to act. The warning may be clear, but the harder question is whether everyone can actually use it. At the coastline, warm water physics meets human decisions, turning a weather system into lived community risk. After landfall, the sea may look calm again, as if the storm machine has simply vanished. But the storm leaves signatures behind mud lines, draining streets, broken branches, and displaced debris everywhere. A puddle on one street connects to cloud bands stretching across hundreds of miles of ocean. No single ingredient builds the hurricane alone. Heat, moisture, pressure, rotation, and organization work together continuously. The quiet ocean is not good or evil. Under the right conditions, it can feed power. So the monster metaphor gives way to something colder and clearer, a machine made by physics. Warm water sends heat and moisture upward, while low pressure gathers air into a growing center. The spiral is not decoration. It is the visible pattern of organized air and moving energy. As pressure falls, more air rushes inward, helping the storm feed itself over favorable warm water. The eye is not safety alone. It is the organized center around which surrounding violence rotates. Many of the strongest form just outside that calm, where the eyewall concentrates enormous energy. When the storm reaches land, atmospheric energy becomes moving water, collapsing trees, and rising rivers inland. That is why the science matters. It reaches homes, highways, hospitals, and difficult recovery decisions afterward. From one flooded street, the view pulls back to ocean, atmosphere, and a rotating planet beyond. Warm water is essential fuel, but a hurricane also needs moisture, instability, rotation, and low shear. The storm is not angry alive or random. It is physics organized at a terrifying scale. The future question is not whether every storm grows, but how much fuel warmer oceans provide. Ocean air, heat, rotation, and coastline belong to one connected Earth system we are still learning. Understanding the machine does not remove the danger, but it changes fear into clearer human attention. The ocean becomes calm again, leaving one question offshore: how much heat waits beneath tomorrow's surface?